Hey, hi guys, this is the video for number 3, and number 3 is the easiest frame you will ever analyze in this course, and I say that because I thought number 3 was quite complicated because I wasn't sure what we had to do with this axial part, and I emailed the professor says you can just ignore the axial part, and if you ignore the axial part, you have a very, very easy problem. It's actually easier than the other two problems have been. And to show you what I mean, the only thing you have to do for this problem, you can break this up into two problems really. Find the deflection of the cantilever due to this force. We're going to treat this not as rigid, but we're going to ignore axial effects, so B can only move sideways. We're going to assume that it doesn't go up or down. It should go down a little bit because if this goes, right, if it goes like this, then my height should decrease a little bit, but we're going to ignore that effect. So we're going to ignore axial effects. If this point goes over this way, point A must move over the same amount. So delta B is the same as delta A. The rotation at A will only be due to this force because this is a hinge. You can ignore the rotation here. You only need to worry about the rotation here. Yeah, so let me show you what I mean by drawing some of this out. We originally have some shape that looks like this, right? Well, this is a hinge. My deflected shape, I have loads that are going down like this and like this. My deflected shape would look something like this. This theta here, this theta A, that theta A is the same theta A that you would get if we had been looking at this problem. This is 20 kilonewtons. These two are the same. What do you actually need to find? Change in angle ABC. Basically, what we're looking for, is going to be, you're going to want to find this angle and do 90 minus those two angles. So for example, if I go back up here, theta A, because of symmetry, theta A and theta B on the left are going to be the same. We have that theta, and we also have this theta, correct? And I'm trying to see here, this should be measured with respect to theta B left, theta B bottom. And this theta ABC is the final theta ABC. So originally the delta theta ABC equals 90 minus that angle, or whatever. If you use radians, it's gonna be what, pi on 2 minus this angle. Whatever angle you get there, just put the right units in there. Okay, so the first thing you want to, when you're actually solving this problem, the first thing you want to do, like you do for all moment area problems, is draw your moment diagrams. Again, if you need help drawing the moment diagrams, please see one of us at this point in the semester. I'm not going to draw those for you, but you should have some m naught here, m equals 0 here, m equals 0 here. So you're going to have moment in this region and moment in this region. You're going to have 0 moment here, 0 moment here, and you're going to have some positive or negative moment here. Once you have your moment diagram, the area of the moment diagram for this section will be your theta b. Right, I could pretend, for example, if it's hard to visualize it this way, you can just pretend that you have two problems here. Pretend that you have a problem like this, and that you have a problem like this, where this is your load. This is what, 10 kilonewtons, and you have something like this. You can treat it like these two problems. In that case, you're going to want to find the theta here, the theta here. You want to find the deflection here. The deflection here will be the same as the deflection here. Deflection here is the same as the deflection here. I shouldn't say deflection, I should say sway. The sway here is the same as the sway here. Sway here will be the same as sway here. Sway is what we refer to as lateral deflection. Deflection by itself, without any connotation, without any extra adjectives, usually refers to vertical deflection. Sway is horizontal deflection. Yeah, so for this problem, we are ignoring axial effects. So for this one, we're just ignoring axial effects in here. You're given E, you're given I, and I haven't checked this out myself yet. But normally we expect, so I haven't checked the solution yet, but normally we expect deflections to be on the order of maybe 1 to 2%. So if you have 4 meters, then 1 to 2% is going to be, this is 400 centimeters, 44, so this is 4 to 8 centimeters. That seems very high. You'd get 1 to 2% if you're talking about, say this building was going under an earthquake. If the building has less than 1% drift, then you normally assume there's a little damage. If you have more than 3% drift, you're going to have a lot of damage to your structure. And construction tolerances, if I remember correctly, are when you're actually building the structure, I think you're allowed to have something like L on 720, I believe. So that's about 0.15% drift, I think. Right, so yeah, so that's going into a little more detail than you need to worry about. You should get an answer that's on the order of centimeters, though. Yeah, and then if that is not correct, you'll see a gigantic post-it on top of this. You'll see a gigantic annotation on this YouTube video. Other than that, I think that's everything for this problem. Let us know if you have any other questions.